Hi and welcome to this new series of video clips. This one is going to be for A2 AQA Thermodynamics, and in this small series we're going to look at the Born-Haber cycles initially, and to do so we're going to use an example of an equation here, and we're going to use sodium oxide formation as our example that we're going to look at in more detail. And for this, you may remember from year 12 that we have something called the delta HF under standard conditions, which is the enthalpy of formation of a substance. And so by definition, the enthalpy of formation of a substance is the formation of 1 mole of that substance in its standard state. So that would be a solid for sodium oxide, from its elements, which would be sodium and oxygen, also in their standard states. And in order to make 1 mole of sodium oxide, we would need 2 moles of sodium and half a mole of oxygen. And so once we have that equation, we need to look at the processes which are involved in more detail and look at some definitions along the way. So what we have to understand and appreciate in the first instance is that sodium oxide is an ionic substance and is made up of sodium ions and oxide ions. And so if we have to get to a situation where we have sodium ions and oxide ions, we have to go through a series of processes which will allow us to make those substances from the starting materials, which in this example is sodium solid as its element, and likewise oxygen gas as its diatomic element as well. So if we look at the sodium example in the first instance, we have to essentially make an ion at some point. And so in order to make an ion, an Na plus ion for sodium, again, if you remember from year 12, we know that we have a process called the first ionization energy. And first ionization energy from your earlier studies is, by definition, the enthalpy change for the removal of 1 electron from a gaseous species forming the positive ion and its electron. And so we have to have sodium also in the gas phase. This will allow us to do that first ionization and produce the sodium ion. Now, in order to get the sodium ion, it has to be in the gas, as we've said, and it has to come from sodium in the gaseous phase. We can see that in our starting equation at the top there, we have sodium present as a solid. And so we have to move sodium from a solid to a gas. Now, this is going to be a new definition now, but this is something called the enthalpy of atomization. And by definition, in this situation, the enthalpy of atomization is the enthalpy change associated with the formation of 1 mole of a gaseous atom. And so if we've got 1 mole of sodium solid going to 1 mole of sodium gas, we have this enthalpy of atomization. You may see symbols such as delta H AT for atomization, and likewise for ionization energy you may see delta H IE, or sometimes you just see first IE written. These would all be under standard conditions, and you'll be given tables of data. And in the next clip, as we move along, we will put all these into some sort of cycle diagrammatical form whereby we can attach the numbers to those. So what we've now done is we've dealt with the sodium moving from a solid in equation number 2 essentially here, and then moving from a gas into its ion in equation number 1. So now we have to try and discuss what's happening to the oxygen. So we know we've got an oxide ion present as the O2 minus ion as a gas, as it will become there. Now, what we've done here is we've added an electron to oxygen. We've added 2 electrons to oxygen to make the oxide ion. When we do so in a stepwise fashion. So we take an electron and we add it to the O minus ion, the O1 minus ion. And in order to manufacture the O minus ion, we must have started with a neutral O atom at some point as well. So we get 2 separate and different processes. These are called electron affinities. And much like the ionization energy, where you can have a first, a second, third ionization energy, what we have here is the first electron affinity, where the first electron is added to a substance, and we have the second electron affinity in that example there, whereby we have 2 separate processes. Like the ionization energy, by definition, these will be gaseous, and so we always need gaseous atoms to start with for the first electron affinity, and then a gaseous ion for the second electron affinity. And that in its turn indicates another equation which is needed. So if we call that equation 3 and 4, we need a 5th equation here, because we started life with a half oxygen gas molecule in our first delta HF equation at the top there, and in order to generate the O gas required in equation number 4, we need to break that covalent bond between the oxygen molecule. This is, again, like it was for atomization of sodium, is the atomization of oxygen. This is producing 1 mole of an oxygen gaseous atom. So it's identical in process to the equation number 2 there. Now, you may also think this is related to something you saw in year 12 called the bond dissociation energy. And it is. But it's slightly different, because the bond dissociation energy would have taken an oxygen molecule and broken 1 mole of the covalent bonds. Breaking 1 mole of the covalent bond would have split 1 mole of oxygen molecules in half, and doing so would have created 2 oxygen atoms. In this example, we only want to create 1 oxygen atom here, rather than the 2 oxygen atoms here. And so you may see in some situations that a question gives you either the delta H AT, the atomization energy, or it gives you the bond dissociation energy. And when we start to draw the cycles, you sometimes have to either half or double a value depending on which one you've got. So for example, if you're given the bond dissociation energy, whereby it creates 2 oxygen atoms and you only need to create 1, you need to half it. So in this example, the delta H AT for oxygen is equal to the bond dissociation energy divided by 2. And if that had a numerical value, you would obviously have to put that into your calculator as such. And so what we've done here is we've now created a series of equations and a series of processes which must take place in order for this top equation, the sodium delta HF formation of sodium oxide. So in order for this equation to take place, we now have a series of other equations which must take place in order for that top equation to happen. And what we will do in the next clip is we will bring these together in a diagrammatical form. We'll put them into their correct, more logical orders, and we'll also introduce the final term, which we haven't discussed here, which is the lattice enthalpy, which quite often is the subject of questions in exams. And what we'll do is we will start to draw that diagram, and we will try to evaluate the lattice enthalpy for sodium oxide and bring this all together into a calculation. And by using all of these definitions, we'll use this as an example in the next clip. So I will see you there when we start to bring this together diagrammatically.